Standard online courses, built on the formula of video lectures followed by multiple choice quizzes, frequently shatter when subjected to the pressures of real world professional practice. This failure stems from a design philosophy obsessed with broadcasting content while ignoring the biological constraints of the human brain. The difficulty of mastering a complex skill is a technical challenge of managing cognitive load, a bottleneck that persists regardless of a learner's motivation or intelligence. Reversing this trend of failed skill transfer requires an approach that prioritizes the engineering of cognitive architecture over the simple authoring of information. This engineering begins with the structural limitations of human memory. Our working memory can only process a few items at once, while our long-term memory acts as a vast interconnected network of automated schemas. Every piece of new information must navigate the narrow working memory bottleneck, which is subject to three distinct types of load. The first is intrinsic load, the baseline complexity inherent in the task and the way its elements interact. Then there is extraneous load. This is wasted mental effort caused by confusing interfaces, irrelevant tasks, or poorly timed instructions. Finally, germane load represents the productive mental energy used to build and automate new mental schemas in long-term memory. The 4CID model provides a framework to manage these forces, optimizing intrinsic load, eliminating extraneous noise, and maximizing germane effort. These three cognitive bottlenecks explain why the four specific components of the 4CID model are required to build professional mastery. The first component is the learning task. These are authentic, whole task problems that form the central spine of the entire curriculum. To manage intrinsic load, these tasks are grouped into classes. Within a class, the complexity remains the same, but the context and data vary. Inside each task class, 4CID applies fading guidance. It starts with a worked example, a fully solved problem with expert logic. Next is a completion task, where learners bridge missing gaps. Finally, they face a conventional task, solving a new problem completely independently. While standard courses often isolate subskills into fragments, 4CID anchors all learning in holistic, real-world tasks from the very beginning. Component 2 is supportive information, addressing non-routine problem-solving strategies and providing mental models so learners don't have to guess. Because this theoretical knowledge is conceptually heavy, it is delivered just in case. Learners study these mental models before they begin a task class, and the information remains available as a permanent reference as they work. In this model, theory acts as a functional anchor for problem solving, rather than serving as the primary focus of the instruction. Component 3 is procedural information, covering routine, step-by-step actions. Delivering these early causes working memory overload. To solve this, procedural information is delivered just in time. This appears as checklists or contextual hints that trigger only at the exact moment the learner needs to perform that specific operation. By separating procedural steps from conceptual theory, 4CIE ensures the learner has exactly what they need without causing a cognitive traffic jam. Component 4 is part task practice. Here, isolated drilling is used exclusively for high-frequency operations that must be performed on pure autopilot. A learner only moves into this isolated practice after they have first attempted that subskill within the context of a whole learning task. Automating these routine actions frees up massive amounts of working memory, allowing the learner to focus on the increasing complexity of future tasks. Moving from psychological theory to a practical LMS interface requires a specific structural translation. Supportive information is placed in a static sidebar or a prerequisite video block, separated from the active work area. The primary window of the interface is reserved entirely for the learning task. Procedural information is integrated through dynamic overlays and pop-ups that appear only when the learner interacts with specific parts of the task. Designing this layout is the result of the 10 steps algorithm, a systematic process analyzing mental models and cognitive rules before any content is built. This interface functions as a functional map of human cognition, aligning the digital environment with the specific ways the brain processes and retains information. Once the architecture is set, the methodologist determines the sequence of escalating complexity. The simplifying conditions approach first starts learners in protected, idealized environments before introducing the chaos of real-world variables. Alternatively, backward chaining has the learner complete only the final step of a long process, gradually absorbing earlier steps until they can manage the entire sequence from start to finish. By utilizing the 4CID framework, instructional designers move beyond simple content delivery to become cognitive engineers, creating frictionless pathways from working memory into deep, lasting professional mastery.